So I'm going to tell you about AMON. Like Fabian said, AMON is based at Penn State. I might remember to mention why it's based at Penn State. So I don't have to, fortunately, I don't have to go through introducing the messenger to these audiences, so I'm not going to do that. I'm going to tell you what AMON is, what is it that we are doing, because I always find it strange that people don't hear about it, so we haven't been doing such a good job as communicating what we do. I will start with what we were planning on doing, what was our ideal of what we want to do, and then I'll tell you exactly what we're doing right now and what the plans are, and I think I have a couple of ideas for what the kids in the audience should be working on. Okay, so this is AMON, so if you ever are in Paris, you can go visit the actual AMON. We use that name in vain, and we call it Astrophysical Multimessenger Observatory Network. And it's based on two main ideas. The first one is changing the paradigm of how we are trying to do multi-messenger. We are trying to do multi-messenger. And so each one of these circles is an experiment, a collaboration, a single messenger, okay? And so if you want to hear every time that LIGO, let's say, has a gravitational wave, you have to sign an MOU with LIGO. So LIGO will send you have an experiment, you and 500 other people have an experiment in gamma rays, and you want to hear every time that LIGO has a gravitational wave, okay? And then if you want to hear about ice cube and you want to see when a neutrino comes in, then you have to go and sign up with an MOU with ice cube, which might seem to you trivial, but again, each one of these things is hundreds of thousands collaborations, okay? And they have to agree on give you their precious data, okay? And usually the way I explain it to people that are not used to work on large collaborations so they understand what this means is that this is equivalent to the Congress in your country, okay? So Congress in your country has to agree on giving out their national secrets, okay? And they have to agree themselves. And now you come with your own country and you have to do a binational agreement that you want to share all these secrets between the countries. Okay, so that's how easy it is. And so usually I use the US, China, and Russia, but here I can say, France, the UK, and Italy, they all want to share three ways, the gravitational waves, the neutrinos, and the gamma rays, and they want to do this, three ways agreement to share their data in real time, and so you can see how easy that is, okay? So that's the naive perspective of what the idea of AMON is, in which you have an MOU with AMON, so you send the gravitational waves, and instantaneously all the people that sign MOUs will get those alerts, and they will send their follow-up of their alerts, and they send their own alerts at the same time, okay? So on your point of view, you can also get a response that sometimes you don't get, because if you send me your gravitational waves and I look with my telescope and I don't see anything, I might not tell you anything because I don't see anything. Instead here, in the MOU it says, if you follow up, you tell me, okay? Even if you don't see anything, because for some of these people, if you don't see anything, that's also important information. So there is also some gain for you to participate in something that makes this much easier, okay? So the three-way here, the neutrino gravitational wave gamma ray burst, if you will, it's natural. I can do this correlation that's as simple as I do the two, as long as everybody signs the MOU. And people might say that's very naive, and I might agree, but that was the idea of how we find the AMON. So you can go to this paper and you would see these. We have a more recent one with what we are. The other important point of AMON is this feature of sub-threshold events. And again, you know, whenever I say sub-threshold to anyone that ever did one experiment, they say they stop listening. It's like, you know, sub-threshold is like crap. Okay, so the example is imagine that you have background events, people call it atmospheric neutrinos, whatever, and you have a signal or astrophysical neutrinos. Okay, and then you have, in your experiment, you have a threshold. And why you have a threshold? Because below the threshold, you're dominated by background, and that is crap. You cannot do anything in there, and that's why you have a threshold. So you look for signals above the threshold. We are interested in this data too, because for you, for your experiment, it's impossible to rescue these neutrinos. This is a signal neutrino, this is an astrophysical neutrino. They are there, but for you, they are impossible to rescue because they are under a pile of atmospheric neutrinos this big and you just can't reach it, okay? But imagine that that neutrino is in time and space with a GRB, okay? And I'm looking at those coincidences with the statistics design a priori that I can tell you exactly what is the probability that that neutrino of this energy, of this level below threshold, it's in time and space with the GRB, and I give you that number, then you can decide how real that is and you can follow it up. Okay? So by making the real-time coincidence, I could rescue sub-threshold events. Okay? And none of the participants individually can rescue any of the sub-threshold signals by themselves. Okay? So that's the key niche, if you will, of AMON. And I'll come back to that later and we can discuss as much as you want. Okay, so those are the two key features of AMON. And there's a lot of experiments that participate, that have MOUs with AMON. You can go to our website and check who signed an MOU. You can look at the MOUs. And you know, some observatories trigger, and you can say why a telescope can trigger, and I'll show you why. And the reason that I said, you know, AMON is at Penn State is because we have people in IceCube at Penn State, we have people in O'Shea, we have people in Hawk, we have people in Veritas, we have people in Swift. There's the control center of Swift. What else? We have a LIGO group at Penn State, and so it makes sense having all these people from those experiments at Penn State to form this group and get together and try to make this new paradigm of multi-messenger triggers. So when we started back in 2011 or so, we needed to learn how to do these correlations a priori, and so we started with a lot of archival analysis. I'm not going to spend a lot of time because I want to show you the real-time analysis, but these are some of the things that we did early on, and this is an example of how an IACT could be triggering observatory. So Veritas, for example, follows up blazars regularly, and the bastards are lucky enough that they catch flares, right? So they are monitoring Mercurial 421, and every once in a while, Mercurial 421 goes boom. And so they sent us all the flares that they have in the archival data of their blazars, the blazars that they follow up. And so we use this block procedure and we established when the blazars were flaring, and then we correlated with the archival data from IceCube. And at that time, IceCube was under construction, so it was the IceCube 40 strings. Okay. The other important point is that all these analyses are done by graduate students that get trained in multi-messenger. So all the graduate students that work in AMON are experts in gravitational waves and gamma rays, gravitational waves and neutrinos and gamma rays and so on. And they get to handle these fun things of approving papers with multiple collaborations, not just one, which is a lot of fun. Okay, so this paper is also about correlation between one FRB and Swift data. This was also dealt by a graduate student, Jimmy, which found this, that, you know, people might get excited, and it was a posteriori, so I wasn't excited. But I think that the other important thing of this paper is that this was the starting point of what Phil showed you yesterday about Wano. This gave us the idea. It was like, we need to download Swift data on the spot, and that's how that started. And Jimmy is one of those people that worked on that system that Phil described. Okay, so this was the analysis of archival data between IceCube and Fermi, also done by a graduate student. So we had, again, I'm not gonna go through the details, but we use archival data from IceCube, and we use Fermi data, that's public, and we did correlations between their events within 5 degrees and within 100 seconds. And we studied we simulated data. The process to do this, I will show you when we do the real time. It's not as simple. We have to generate scrambled data, study that, make sure that that makes sense, and then look at the data for real. And you can look at that paper. But so the end was that we did the archival analysis between IceCube and Fermi, and then when we published that paper, Antares came to us and said, you know, here's our neutrinos, do the same analysis with our data. And we said, you know, Fermi's public, you can do it. Say, no, you already did it, you know how to do it, here's our data, do it. And so then we started receiving, not only we did the analysis with Antares data, which is published here, we also started running the real-time analysis, Antares Fermi, at that time until they decommissioned in February of this year. This is the first analysis that we started in real time. So we started working. So this is, so far I just talk about coincidences because that's what AMON is about. But because we are receiving all the data from these experiments, it's easy for us to set up. So it's easy for me because I don't do it. I got people for that. But it's easy for us to just say, you know, IQ says, you know, above a certain threshold, just send it to everybody. Above this threshold, send it to Fermi because we have an MOU. And we can handle all sorts of things. So it's also easy for the experiments to tell us, you know, what they want us to do at the different levels, what they want to make public, what they want to make private, to whom, special MOUs with other people, whatever you want. So we are the pass-through, we don't do anything, which is, you know, we come the data and we said, you know, IceCube saw this. And so we started sending those in 2016. And then because we send this, we had a lot of these Swift proposals that also you heard yesterday. Most of our Swift proposals all of our Swift proposals are run by our postdocs, so they get experience putting proposals and getting money of their own. And you heard about this, so this is the typical example of the AMON notice. And I think that the interesting part of this, okay, so there it goes. It's not in real time. Yeah, the important part of this is that from the time that they triggered in Antarctica until the alert came out, it was 42 seconds. So there you got the neutrino. And you know this whole story, so I'm not going to spend any time in here, except that I want to make the point that I think we, as a community, should get out of this paradigm of relying on someone saying, oh, I think there's a galaxy in that area, or, you know, because we got this alert, and then someone said, oh, there's this laser that's been flaring in Fermi, but it's been in a high state for the last 2 months and so on, and then people go see it. We need to get out of this. We need to get in something. So that's something that the young people should start working on yesterday and try to get a new paradigm in which we get things a priori and not a posteriori. We can talk about the gravitational wave event, and it's kind of the same thing. So you can see that everybody follow it up, and it's a beautiful correlation, but it's a 3 sigma. So, and see, look at this. Anyway, so that's my comment for the next part of the workshop. And like I mentioned, so we are sending this pass through, and then we are following up with some of these Swift proposals. We get a few per year that are followed up by Swift. And so this is what we're doing now. We're trying to do as many real-time coincidences. So these are the first multi-messenger alerts. Okay? So it's not from a single experiment. These are coming from AMON. These are the alerts that we are producing using sub-threshold data. Okay, so each experiment, and this we have to work together with all the experiments because we don't analyze your data, we don't decide any thresholds, and so we need to work with the experiments. You define what sub-threshold is for your experiment. So this is what Hawk decides it's a sub-threshold. So Hawk has this field of view every day. So this is a month of data, but every day you get this field of view, okay? And they look at that data for the day, and they say, there are these excesses, these are random excesses, okay? And they send their own alerts if they get an excess above 5 sigma or something like that. But if it's above 2.75, and again, why 2.75? Because they defined that 2.75 was okay for them. So we take 2.75. They send it to us, okay? So again, these are sub-threshold, okay? So if you ask anyone in Hawk, there's nothing exciting in there, okay? And these are the tracks from IceCube, and again, this is sub-threshold, but it's a month of data, okay? So the same month of data. So here is where it comes all the work that we have to do. We use this data to produce scramble sets of both experiments, okay? And then we use that scramble data to determine the correlation probability, okay? So we use the probability that Hawk send us, the probability that IceCube send us, that would be multiple neutrinos correlated in time and space with gamma ray excess, and we determine the p-value of the correlation. And then, so we use this ranking statistics, so this is the chi-square, and this is, so you take that map from Hawk, you take that map from IceCube, and you say what correlations are, and say all the time there are, thousands of, tens of thousands of correlations, sure. And then you determine what is the threshold, and again, this is something that both IceCube and Hawk has to agree on. They determine what is the correlation level that they want to do for their coincidence analysis. And they say, okay, we want to see a level of 1 per year. Okay, so 1 per year is this value of the chi-square. So I go to the chi-square here, and I cut here. Okay, so these are the events that I'm going to send. Again, this is all scramble data. So I can generate as many years of data as I want, because it's just made up data. Now, I use these. Once they both approve this analysis, they are happy with what we did, they ask as many questions as they want, and then we compare with the real data. Okay, so these are 3 years of both experiments that we're running at the same time. I think that this was, I can't remember, 2015 to 2018 or something like that. And then you compare, so the blue line is what I showed you in the previous slide, but scaled to 3 years. Okay? And then the red one is the real data from IceCube and Hawk for those 3 years. So as you can see, the scrambled data reproduces the trend of the real data, which is that you use their data, but it's good. It's a fuzzy feeling that you get something like that. Okay. Then you look at the 1 per year threshold, and you get 2 or 3 events above that threshold, which is exactly what you expect, because again, we put it at 1 per year, we run for 3 years, there should be on average 3, but this is Poisson, so who knows, but those are those 3, okay? Again, you could say, well, those 3, there's nothing to get excited about. It's like, yeah, I know, but it's only 3 years of this, and we have 1, blazar neutrino after 10 years of data, so it's not that we're, that we have millions of discoveries every day, so we have to be patient. But now this is running in real time, okay? And we can send them alert in whatever threshold value they are happy with. And this value comes in with the alert, right? So when you receive it, if you receive this guy is this guy, which is once every 38 years. And so this is what you receive. You receive this value of the false alarm rate. And here is the coincidence best location using the neutrinos. The neutrinos are the black dots with their uncertainties. The uncertainty of the correlation of the coincidence is dominated by the Hawk uncertainty region, because Hawk is smaller than the neutrino location. But this is what you get. And you have the paper for the archival analysis that we did. These are the rates of how much data we are getting, and this is the rate of coincidences that we have per day. And again, we send them, I think that for the archival, we did 1 per year, and the real time is set up for 4 per year or something like that. And so, like I mentioned, we serve as a pass-through. So Hawk has its own GRB sub-threshold triggers. We use it for our internal analysis, but then we send whatever level they want. So if they set up 1 per year, that's what we send to GCN. And again, this is just like IceCube alerts. It's a pass-through. It's a Hawk alert. So this one that I show you is the IceCube Hawk alert. It was the first multi-messenger trigger between neutrinos and gamma rays. That's another example. And we have several new pass-through channels that we're sending. So these are the alerts that we sent. Like I said, the threshold was set up at 4 per year. There were 7 coincidences found in the archival data, because until February, between 2020 and 2022, February of 2022, we also ran the Antares Fermi that I showed you at the beginning when we did the Antares Fermi archival. Then we set up the real time. So until February, we were running 2 multi-messenger triggers, Hawk, IceCube, and Fermi Antares. And now Antares decommissioned, and we are trying to work with KM3Net to get coincidences from them as soon as they start sending alerts. And I get only 1 minute, so I'm going to try to finish this part. We are sending the first truly multi-messenger trigger alerts. We keep sending all the pass-through notices from IceCube and now Hawk. We get data from cosmic rays. We can discuss what that is. The data from Hawk, IceCube, and we're also working on the next 04 in correlation with Swift, but that's not strictly an AMON MOU. It's just a group of us with LIGO. That's the word, the way LIGO likes to work. But we are working on that too. Okay, so I told you all of this. You can have the slide. I think that what is important is that I think that we need to change the way we are doing these multi-messenger triggers. We in AMON, we are working on our next point, which is having more theoretical motivated searches, not just coincidences of data streams that we get. I think that they are important and we should do them, But I think we are also trying to add to that. We're not going to change. We're trying to add theoretical motivated searches. And I think that the other point that I would like to add for the young people, I think that we need to also start thinking for the next generation. You might think that it's too early, but one day we will have Gen 2 kind of neutrino telescopes. We will have LISA kind of interferometers, and the amount of data will be overwhelming. And there'll still be subthreshold events in there, and there will still be a point in making real-time multi-messenger coincidences that are going to be important to determine what events are actual real events. So thank you.